in class, if you have any questions, use the chat box, or you can pipe it in on your mic. And like I've done all semester, I've been working a ton on your exam prep, making sure that you guys are as prepared as possible to do well on your exam. So we're going to do floods today. And in your reading and in your lab this week, oh, if you have any lab questions, please type those in and we'll make sure and address those as well. It talks about how frequently we see flooding, and they are the most common disaster that you'll see is a flooding disaster. And looking at the river systems of the world, you can kind of see why our landscape, when I taught geology, I talked to them. We had only maybe a couple weeks left, and we had lots of chapters we hadn't gotten through. So I said, you know, what do you want to study? And they were really interested. They wanted to understand as much as possible why the world looks the way it does. And I said, okay, then we've got to do river systems and river erosion, because that is the biggest factor that's defines our landscape. Is like our beautiful country is has been carved by the river systems, and they're kind of the biggest factor in understanding why our rocks and landforms look the way they look. I mean, there's other stuff too, but river systems are incredibly important. So when we talk about a river system, often we talk about drainage basins. And essentially, a drainage basin is just all of the tributaries that feed into a specific river. And the size of the drainage basin is really important when we're looking at rivers to talk about their flooding potential. So what do you think here? A better question would be, how does the size of the drainage basin factor into the potential for a flood? So if we're looking at a specific river system and we're doing some sort of analysis, you know, what is the probability of a specific type of flood in this area? The size of the drainage basin is really important. If it's a big drainage basin, it means there's more tributaries, more water flowing into the river system, and a higher risk for high discharge floods, which are the most damaging and the most erosive. So it makes sense. If there's a lot of stuff feeding into a specific system, then there's the potential for a lot of water. If we look at river systems kind of in a really big view, you know, we look at the tributaries, they're often in mountainous regions, and then the river eventually works its way to the ocean. That's kind of how all of them look, this basic idea. The reason I put it up here for this class is because as a system moves from the tributaries down to the ocean, it changes in type. So in your reading, it talked about meandering river systems versus braided river systems. And that doesn't mean like one river, like the Mississippi River, is only a meandering river, or it's only a braided river. That's not true. It depends on where it's at. So if we look kind of here, this area right where it starts to level out, this is where we would see our braided river systems right as the high energy moves from the mountains to a flatter valley. And then as the river continues along a flat valley is when it starts to meander. So there's other types of river systems, but in this class specifically, we only worried about too. Meandering rivers versus braided rivers, and specifically we're looking for their flood potential. Since we're a disaster class, we're looking at worst case scenario. So meandering rivers form when a river travels across a flat land. So the slope is incredibly important in determining what type of river system we're going to have. So a meandering river is where it's flat. So it meanders, which means it wanders back and forth across its floodplain. And I liked this little video about why rivers curve, and we're going to start it. Maybe we'll just do the whole thing.
Compared to the whitewater streams that tumble down mountainsides, the meandering rivers of the plains may seem tame and lazy, but mountain streams are corralled by the steep walled valleys they carve. Their courses are literally set in stone. Out on the open plains, those stony walls give way to soft soil, allowing rivers to shift their banks and set their own ever-changing courses to the sea, courses that almost never run straight. At least not for long, because all it takes to turn a straight stretch of river into a bendy one is a little disturbance and a lot of time. And in nature, there's plenty of both. Say, for example, that a muskrat burrows herself a den in one bank of a stream. Her tunnels make for a cozy home, but they also weaken the bank, which eventually begins to crumble and slump into the stream. Water rushes into the newly formed hollow, sweeping away loose dirt and making the hollow even hollower, which lets the water rush a little faster and sweep away a little more dirt, and so on and so on. As more of the stream's flow is diverted into the deepening hole on one bank and away from the other side of the channel, the flow there weakens and slows. And since slow-moving water can't carry the sand-sized particles that fast-moving water can, the dirt drops to the bottom and builds up to make the water there even shallower and slower, and then keeps accumulating until it becomes new land on the inside bank. Meanwhile, the fast-moving water near the outside bank sweeps out of the curve with enough momentum to carry it across the channel and slam it into the other side, where it starts to carve another curve, and then another, and then another, and then another. The wider the stream, the longer it takes the slingshotting current to reach the other side, and the greater the downstream distance to the next curve. In fact,
Okay, so I didn't think in the reading it explains super well how meanders form or why they start bending. So I liked that quite a bit. In your exam test bank, it has this question, why do rivers curve? And the way that it's worded in the exam is that we get meandering rivers when the land is so flat, there isn't a distinct direction of tilt to guide its flow. So in the video, it talked about how there's erosion on the outside of a curve and deposition on the inside of the curve. That's really important. There's several questions in the test bank about meandering rivers and where erosion happens, and specifically which side of the meander would be the most dangerous to build a home. So if we're looking at the diagram, it's the outside of the meander that is the cut bank. That's where there's the most energy, and that is the most dangerous place to build, because eventually that's going to erode away from your foundation and you get left like this poor family in Massachusetts. And you can apply this to successful river floating this summer. I have like 25 river tubes, like the good ones. And we go every year and we float down the Provo River. And understanding how meanders flow is clutch to getting down fast because the water's cold. And you always try to position your tube so you're on the outside of a curve, because that's where the water is flowing the fastest. This is how it's phrased exactly on your exam. The fastest water in the meandering river is located on the outside bends. So erosion happens on the outside, deposition happens on the inside. And over time, we get the beautiful meandering shape of a meandering flow. So where not to build? Above a cut bank, always. Also, where not to build? On the floodplain. And as far as floodplain terminology, there's some important distinctions. The hydrologic floodplain is where the river's flowing, the current flow, but on your exam, it only asks about the topographic floodplain. And there's a couple bullets we'll go through. So a topographic floodplain is the elevation above the river banks. It's flat, has significant rise at its edges. And this, I think, is the best way. It's formed over centuries by repeated flooding and erosion. It marks the typical maximum of large floods. So a topographic floodplain is created over time. It's over and over and over, marks the edge of the big floods. On the Mississippi River, and this is from your reading, we have this would be the hydrologic floodplain here where the Mississippi River is. The levee floodplain, so this is what it's been corralled into, gives it this much room, but the topographic floodplain or the historic floodplain is this whole area through here. It's much wider. And often I still, driving around, I always look for the topographic floodplain because I always just do. When I see a specific profile, I find the topographic floodplain. I guess in my mind, I think, okay, if there's a disaster, I'm going to go up there. I like this another visual of how this kind of evolves. So this is Idaho. And so the topographic floodplain is this area up here at the top where it's flat and it marks the edge of, the historic floods of the river. The other type of river system was a braided stream. They form when streams become choked with sediment. And so they form, like I showed you, right where the topography gets flat. And they no longer have the velocity because they no longer are roaring down the canyon. And so they have to deposit the sediment and it just kind of gets deposited and then the river has to move a little bit and then more gets deposited. And over time, it just forms these profiles, the braided stream. It happens where there's a locally abundant supply of sediments. The most beautiful braided stream systems form at the base of glaciers, where there's all of that pulverized rock that the glaciers eroded. We call it glacial flour. And it's right at the base where there's all the melt, and it just forms these beautiful braided streams. They don't meander. And when you kind of look at them, sometimes you're like, well, it looks like a bend, but notice that it's just like a thin part of the river that's bending. It's not the whole thing. So we would say that these bends are not meanders because their bends are formed much differently. It's not that, like we saw in the video, that kind of process where there's some sort of disruption and eventually it starts to bend and it kind of changes where the fastest part of the stream is. It's not like that. Braided streams are dynamic. They change constantly. Braided streams are fast. They have a lot of sediment. They carry big rocks. So they're more damaging typically than meandering streams. So this relationship here is important. If it's a fast river, that means it can carry big rocks, which means that those big rocks can, you know, collide with anything in its path and destroy stuff. So fast river, big rocks means lots of damage. So the comparing the two, and this is key to understand these relationships because there's just several questions on the test bank. I think there's more questions about this specific thing, meandering versus braided, than any other concept in the test bank. So meandering rivers are slower. They have a smaller load, which means that they carry smaller things because they're slower, so they have less energy. And there's more sedimentation. Braided rivers are faster, they carry larger rocks, and so they're more damaging and more erosive. And look, this is one of the glacial braided rivers, this image here. So beautiful from space, or not from space, from an airplane. Most fatalities in flooding happen when people drowned in their cars. So the number one thing, honestly, that I hope you get out of this class is never drive on a flooded road, ever. Even if it's a road you have driven on every day of your life, you never know if there's been erosion on that road. And most people that die in a flood die in their car because they drive on a flooded road and they didn't realize that the river had eroded out all the stuff that's underneath it. And this number 2 feet of water can float a car. There's an exam question that asks specifically, how deep does it have to be to float a car? And it's 2 feet. This is what NOAA puts out, never flood. Turn around, don't drown is their slogan they have. A flooding feature that's talked about are alluvial fans. Here's a beautiful one from Death Valley. You can see why they're called fans. They have that beautiful fan shape. They form from multiple flash floods. So this is, again, similar to braided streams where the slope goes from being in the mountains to hitting the valley, so it loses all of its energy and it deposits everything that it's carried. And so these alluvial fans, they build up over time by repeated flash flooding. Alluvial fans are also dangerous places to build homes because they're right where the stuff from a flash flood gets slammed into the ground. Here's another one. This is feedback from your reading. I think they're beautiful. All of these are like pictures from the desert because that's where we can see them the best. They're not obscured by, those meddlesome trees and vegetation and such. In terms of like this type of terminology, the only thing that's on the exam test bank is discharge units. So the units of discharge is cubic feet per second. That's it. Makes it easy. 100-year flood. This is probably the least understood concept and the one that students have the most misconceptions about. So let's talk through it because there's a few questions about this. 100-year flood, and you have a lab question about this. 100-year flood is a statistical device used for insurance. It is specifically the highest flood of the past 100 years or a projection of what that flood might be if a long enough record is not available. Essentially, there's a 1% chance of a 100-year flood every year. So the phrase of this is so confusing. 100-year flood. That makes it seem like, okay, well, we're going to have one of these once every 100 years. And that's not it at all. Actually, what it is the magnitude of the flood. And I like this graphic here. Essentially, it's a flood line. So at this point, like if we're looking just at this image, if the water level got up to here, then it would be a 100-year flood. That's the magnitude of it. It's a 100-year flood. And because it's not any kind of recurrence interval, it's not predictive. We're not saying, okay, well, you only have one 100-year flood every 100 years. All they're saying is, this is how high the flood level got to. This is the magnitude. Instead of, it's a magnitude 7 earthquake, we're saying it's a 100-year flood. That's the magnitude. There's other terminology. There's 500-year floods. There's 10-year floods. There's 1-year floods. There's 1,000-year floods, 10,000-year floods. It's just the magnitude. And every river system will have its own 100-year flood level. Now, I'm sure you have questions, so go ahead and get your mic and ask me if you need kind of clarification about what this means.
Do I need to raise my hand?
Nope, you're
okay.
not.
So the 100-year flood in the lab, there's a question about the 10-year flood and the likelihood of that happening. So is that, I'm like, is that a 10% chance of it happening every year for 10 years?
Yep. Not for 10 years. There's no...
just the 10% chance
10%
every year
chance.
of it happening.
Exactly. 100-year flood, 1% chance. I don't really love... that kind of confuses the issue a little bit because it seems sort of predictive. But it's just historically, if there's been records long enough, they look, okay, this is the highest flood every 100 years. So we're going to say, because it's a statistic, 1% or this flood level. Did that answer your question, Abby?
Yes, I just wanted to clarify it.
Perfect. Yeah, and Crystal's, I moved the group chat over because I couldn't run the PowerPoint and have it up on the screen. She said, we had a 100-year flood 3 years in a row in Houston. Yes, absolutely. That happens all the time. And people get really confused, like, oh, that means that we're like having the worst luck ever. And it like gets everyone really anxious. And I mean, that's pretty unlikely. There's a 1% chance every year, and you had it 3 years in a row. But the truth is weather systems are so unpredictable. And like, I teach oceanography right now, and we're talking about like all of the Earth systems that are connected. Specifically, we're looking at like air-water connections and how the temperature of the water affects all of our atmospheric currents, and how even plate tectonics affect atmospheric currents. And it's all so interconnected that there's just no way to predict things that have to do with the weather. And so we do the best we can. And again, it's just for insurance. So we're just trying to, what they're really looking at is deciding if they're going to insure a home, depending on where it's at. So if you have your home on a 100-year floodplain, then it's pretty unlikely that you're going to have a flood. But if you're on a 10-year floodplain, that risk is much higher, and you may not be able to get flood insurance at that point. Who else? Does anyone else have a question, or maybe want to clarify something?
Can I ask a quick question?
Yeah.
So on the lab, it asks like you look up your like where you live, your home,
Mm-hmm.
and to see what the flood map is. And it says like in my area where I live, there's no flood map.
Yeah. That's okay.
I mean, I looked at other areas, it was fine, but
right.
So unless it is a flood area, do they not map it?
No, because everywhere has a risk for flooding. Okay. Because I've run into that too, because I've looked in my area to see, what floodplain am I on? And like our thing is my number one hazard is liquefaction from an earthquake. So most of the government funding and stuff is doing research for that. And so like certain areas, more research is focused on flooding, and like the way the information's dispensed is different between each state. And so there's probably flood maps available. It just is trying to find them when you're like dealing with government bureaucracy stuff.
I just went to our local, I just went, because we kind of live out of town a little ways, and so I just kind of just did the city.
Mm-hmm.
So
right, that's perfect. But yeah, not everybody will be able to find that, but hopefully they can look somewhere that they like or grew up in, or where their grandparents live, and they're able to see. And like my area is having a big survey done for our flood risk, and so they will continue to be updated, and more people will be able to access that information as we get better at keeping records digital and all that stuff. Great comment. I'm glad you brought that up. Flood mitigation. There's just a couple of things talked about what effects urbanization has on flooding. And essentially, when there's a lot of impermeable surfaces, then when we get heavy rains, there's nowhere for the water to absorb. And so in these areas, water moves faster and the floods are higher than in more rural areas. So urbanization means the water moves faster and the levels are higher because there's not as many places for it to be absorbed. Um, the exam states that the best mitigation is just to stay out of rivers' natural systems, and kind of, I think we talked about this last time, landslides. That's fine. That's a fine attitude for when we're in the Western United States and there's places where you don't have to be in a flood plain, but that's not always possible. So I think this is kind of, I mean, that's true. The best mitigation is just to stay out of the way, but I know that that's not the end answer. I talked about dams and flood mitigation, and it wanted to make sure and make the point that sediment gets trapped in dams and eventually fills up the dam. And I don't know anywhere where that's happened. I mean, I'm sure it's happened. It makes sense. The sediment can't travel down. It gets trapped there. I don't know that that's the biggest risk, but that's on the exam. So I wanted to share that. As far as insurance, are floods covered in your insurance policy? And hopefully from your lab, you've seen that no, flood is never covered in a homeowner's or a home insurance package. You have to purchase it separately from the government. And then I haven't gotten the case study stuff put together yet. The case studies aren't posted yet, and well, that hasn't even opened yet to start them. But I will kind of put together, just like I've done for the other weeks, some guiding concepts to make sure that you remember for each case study. And I'll post that in the class. If you go to the course and then to content, exam prep, you will see it. So let me go there now just to make sure everyone knows where it is. So if we go to content, class meetings, exam prep, it will be here. So we'll have tonight's class meeting posted there, and also the study guide, and you will have all the information you need. So that's what I have for flooding exam prep. I'm so glad you guys could come tonight, and you are free to go, and you've earned your opportunity for a retake. But if you have any additional questions, please ask them now, and I'll be happy to answer them.
Is there a time expiration when we can go back and redo a lab?
Honestly, not really. I used to say, don't do them all the last 2 weeks of class, but I've never had students asked to do a bunch at the end anyway. So I know sometimes there's special circumstances, but nah, you can keep them and wait till they're done. That's totally fine.
All right. Thank you so much.
Yeah. Have a good night.
You too.